The internet has revolutionized our world. It connects billions of devices across continents. This complex network relies on a set of rules called protocols. These protocols govern how data travels across the globe. At the heart of this system lies the TCP/IP protocol suite. Think of the internet as a vast postal system. Data is carefully packaged into envelopes before being sent off. The TCP/IP suite defines these envelopes and the rules for delivery. It's a layered architecture, with each layer having a specific role. Imagine a carefully orchestrated assembly line. Each layer adds its contribution to prepare the data for transmission. This layered approach simplifies the process and ensures compatibility across diverse networks. This essay focuses on a crucial layer of the TCP/IP model, the Internet Protocol IP. It's the layer responsible for addressing and routing data packets across networks. The Internet Protocol, IP, is like the postal service of the Internet. It defines the addresses used to identify devices and the rules for delivering data packets. Each device on the Internet has a unique IP address. It's like a home address for your computer or smartphone. When you send data, it's broken down into small packets. Each packet carries the source and destination IP addresses. Think of these packets as postcards with the senders and recipients' addresses. IP operates at the network layer of the TCP/IP model. It doesn't concern itself with the content of the data. Its primary job is to ensure that packets reach their intended destination. IP is a connectionless protocol. This means there's no established path between the sender and receiver. Each packet travels independently, potentially taking different routes. An IP packet is like an envelope containing your data. It has two main parts, the header and the payload. The payload is the actual data being transmitted. The header contains essential information for routing and delivery. Think of the header as the address label on our envelope. It includes the source and destination IP addresses. It also has information about the packet's length, version, and type of service. The header also includes a time to live, TTL, field. This field decrements at each router along the path. If the TTL reaches 0 before reaching its destination, the packet is discarded. This mechanism prevents packets from endlessly circulating on the internet. Another critical field is the checksum. It verifies the integrity of the header data. Any corruption during transmission can be detected using this checksum. Encapsulation is a fundamental concept in networking. It's the process of packaging data from higher layers into lower layer protocols for transmission. Imagine placing a letter, your data, inside an envelope, the IP packet. The data starts at the application layer. It could be an email, a web page, or a video stream. This data is then passed down to the transport layer where it's segmented. Each segment receives a header, TCP or UDP, for reliable or unreliable delivery. These segments are then passed to the network layer IP. The IP layer adds its header, creating an IP packet. This packet is then encapsulated into a frame at the data link layer for transmission on the physical network. This layered encapsulation ensures that data from different applications can be transmitted over a shared network infrastructure. It's like having standardized shipping containers that can be transported by various modes of transportation. Section 5. The journey of a packet routing and forwarding. Once an IP packet is encapsulated, it embarks on a journey across the internet. Routers act as the postal workers of the network. They determine the most efficient path for packets to reach their destination. Routers use routing tables to make forwarding decisions. Think of these tables as maps that guide packets through the network. When a router receives a packet, it examines the destination IP address. It then consults its routing table to find the best outgoing link. Routing algorithms are used to create and update these routing tables. These algorithms consider factors like network congestion, link speed, and distance to optimize packet delivery. The Internet's robustness lies in its decentralized routing infrastructure. If one path becomes congested, routers can dynamically adjust their routing tables to use alternative routes. This self-healing capability ensures that data can often find a way to reach its destination, even in the face of network disruptions. Section 6. IP addresses, the global positioning system of the Internet. Every device on the Internet needs a unique identifier. This is where IP addresses come in. They act like the GPS coordinates of the digital world. Without IP addresses, communication on the Internet would be impossible. Currently, we use two main versions of IP addresses, IPv4 and IPv6. IPv4 uses 32-bit addresses, providing around 4.3 billion unique addresses. IPv6 uses 128-bit addresses, offering a vastly larger address space. Each IP address consists of two parts, the network address and the host address. The network address identifies the network segment the device belongs to. The host address identifies the specific device within that network. IP addresses are crucial for routing and delivery. They allow routers to determine where to send packets, ensuring they reach the correct destination network and device. The transition to IPv6 will accommodate the ever-growing number of Internet-connected devices. Section 7. The unreliable nature of IP, embracing imperfection. IP is a best-effort protocol. It strives to deliver packets but doesn't guarantee delivery. Think of it as sending a postcard. There's no guarantee it will arrive. This unreliability might seem like a design flaw, but it's a deliberate trade-off. Guaranteeing delivery for every packet would require a lot of overhead. It would slow down the network and add complexity. IP prioritizes speed and efficiency over absolute reliability. The higher layers of the TCP IP stack, like TCP, can provide reliability if needed. They implement mechanisms like error detection, retransmissions, and acknowledgements to ensure data arrives intact and in order. This separation of concerns allows IP to focus on its core functionality, addressing and routing. It leaves the responsibility of end-to-end data integrity to the higher layers, which can tailor their services based on application requirements. Section 8. Fragmentation and reassembly navigating network constraints. Not all networks are created equal. They have different maximum transmission unit or MTU sizes. This MTU defines the largest packet size that a network can transmit. When an IP packet is too large for a particular network, it undergoes fragmentation. Imagine trying to send a large package through a narrow doorway. You would need to break it down into smaller pieces to fit through. Similarly, fragmentation divides a large IP packet into smaller fragments that can traverse the network with a smaller MTU. Each fragment becomes its own IP packet with its header. The receiving device then reassembles these fragments back into the original packet. This process ensures that even large amounts of data can be transmitted over networks with varying MTU sizes. While fragmentation is necessary for interoperability, it does add complexity and overhead. If even one fragment is lost, the entire packet needs to be retransmitted. This highlights the importance of having efficient fragmentation and reassembly mechanisms. Section 9. Unveiling the secrets of IP packets with Wireshark. Network analysis is essential for troubleshooting, security, and performance optimization. Packet sniffers are invaluable tools for this purpose. They capture and analyze network traffic, providing insights into the flow of data. Wireshark is a popular and powerful packet sniffer. It allows you to capture packets in real time and examine their contents in detail. You can filter packets based on various criteria, such as IP address, protocol, or port number. By analyzing IP packet headers and payloads, you can gain a deep understanding of network conversations. You can identify bottlenecks, security vulnerabilities, and application behavior. Wireshark is an indispensable tool for network administrators, security professionals, and anyone interested in the inner workings of the Internet. Section 10. The importance of understanding the IP layer. The IP layer is the backbone of the Internet. Understanding its workings is crucial for anyone involved in networking, security, or Internet technologies. It provides the foundation for all higher-level protocols and applications. Knowledge of IP addressing, routing, and packet structures is fundamental for configuring and troubleshooting networks. It enables you to diagnose connectivity issues, analyze network performance, and optimize data flow. Furthermore, understanding the IP layer is essential for network security. Many attacks exploit vulnerabilities in IP implementations. By understanding how IP works, you can better protect your networks and systems from these threats. In conclusion, the IP layer is a testament to human ingenuity. It's a robust and scalable protocol that has enabled the creation of a truly global communication network. As we continue to rely on the internet for more aspects of our lives, understanding the principles of IP will become increasingly important.